So let's begin our session for today. Let me just present my screen. So am I audible and is my presentation visible? Okay, yeah, just a second. So welcome to the week 7 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL SWAYAM program. Myself Pratyumnan from the Department of Chemical Engineering, IIT Guwahati, Assam. I am usually responsible for conducting the live interaction session for this course. So we are in week 7 of the course, or you can say we have also come almost towards the end of this waste to energy conversion routes. So we have traversed across for the last 6 weeks related to the production of energy from various types of waste material, and we have also seen the different types of routes for the conversion of the waste. Starting from thermal, we have learned about the different types of process that is utilized, about the various kinds of strategies to derive energy from the waste material, and we have also seen the advantage and disadvantages of the thermal conversion routes, and in each of them we have individually seen their advantage as well as disadvantage. After which we are currently, from the last week, we are focusing on conversion of waste to energy through biological routes. So in biological routes, as all of you can recollect, we talked about the anaerobic digestion process, and we also talked about the fermentation of ethanol. So let's revisit that slide. Yeah. So this is what we were mainly focusing during the last class, the biological conversion routes of conversion of organic waste or biomass based waste to biogas. So for that we do anaerobic digestion process. I hope everybody knows what is anaerobic digestion process as such means, and I mean the difference between that and aerobic digestion process. Is there any ambiguity in that particular term? So we talked about how to convert this biomass to biogas through anaerobic digestion process using the help of microbes in the presence or in the absence of oxygen. So we get biogas and also other impurities. So those impurities, for example, hydrogen sulfide, siloxanes, which needs to be removed before the gas is let out into the atmosphere or basically utilized for any other purpose. Then after that we also saw something related towards converting the biomass based waste or lignocellulosic biomass based material for the production of biofuels, or you can also say alcohol production. So that is through fermentation process. So we saw how to take this kind of hexose molecules, or what you call as glucose, and then use some sort of the microorganism and ferment them to basically produce the ethanol, and then the ethanol that is produced through this process is further concentrated through distillation, wherein you get around 95 percentage of the pure ethanol. To make it more what do you say, concentrated or pure, you further do some sort of a dehydration technique, wherein the water molecules are removed to produce the concentrated or pure ethanol, so that that particular ethanol can be blended with other fuels such as gasoline, so that the energy efficiency of the fuel can be improved. So and then we also saw about if you guys remember the different types of microorganisms that can be used for this ethanol fermentation process, and many more. And in between these two concepts of anaerobic digestion and ethanol fermentation, we saw some a relatively new concept on microbial fuel cells. So I hope we had an extensive discussion during this about this in the last class, where we discussed about the fundamentals of microbial fuel cell, the basic mechanism. So this is the mechanism. I hope everybody are able to recollect about what we discussed and how the microbial fuel cell is different from the hydrogen fuel cell. And we discussed about the factors, the catalyst, the anode, the components of the fuel cell basically. So apart from that, we also discussed about the types of membranes that is used in the fuel cell. For example, the Nafion, uh, which is nothing but the perfluorosulfonic acid membrane. How does the H plus ion travel through these membranes? Through some sort of a mechanism so called as Grothe structural diffusion mechanism. I hope people are able to get what actually this mechanism means. So can anybody quickly tell me how does this H plus ions get transported through this mechanism, like the explanation of how this ion transportation takes place? Yes, anyone?
Oxidation takes place at anode.
No, no, no. I'm asking about that H plus ions that gets produced through at the anode. How does it travel through that membrane? So, in the last class, we saw something so called as the H plus ions. They usually go through a hopping mechanism. So, let me just quickly go through that. So, you have this SO3H groups as the pendant chain. So, you have the PTFE backbone, and to that backbone, these SO3H chains or groups are attached. So what happens is this Nafion is actually, we have to use it in a hydrated form. So when that is present in the hydrated form, it is usually present as SO3 minus and H plus. So it will be something like this. So when the H plus ion comes in, so when the H plus ion that is produced at the anode, that is this H plus ion, which is produced at the anode, this comes in contact with this SO3H group, and this H plus ion kicks out this H plus ion from its original site and occupies that space. The H plus ion that gets kicked out at the first point goes to another SO3H groups which exists similarly as SO3 minus and H plus, and then kicks that from its own place. So like that, this keeps on happening throughout the thickness of that Nafion membrane, and at the end, one H plus ions which is there as a part of this SO3 minus and H plus groups gets kicked out. So that H plus ion that gets kicked out at the end of the membrane is what going to participate in your cathode reaction, which is this H plus. So it's something like a kind of a hopping mechanism wherein the H plus ion goes and attacks the other H plus ion from its original site, which then moves and then kicks out that again, and then again that kicked out H plus ion moves to another site, third site, and this keeps happening, and then that H plus ion at the terminal gets kicked out, or comes out of the membrane, which then reacts with the oxygen at the cathode to produce water molecules. So, I mean, is there any confusion here? This, because this we discussed last class also, but so if you have anything to ask, then you can ask right now, or fine. If you have anything then related to this, then we may discuss at the end also. So that won't be an issue, I think. So this is with the what we did in the last week session. In today's week 7 live interaction session or the course content, we are specifically interested towards learning on how you can derive energy or extract energy from the same lignocellulosic biomass based waste material, but through fermentation, that is what we are going to continue, and through transesterification reaction. So speaking of the fermentation reaction, what we are basically concentrating in this week is about the calculation of the yield of ethanol. That is, if I'm going to use some amount of sugar, how much amount of ethanol I'm going to produce, the yield, and then we are also going to concentrate on something so called as the quantity of uh, ethanol that is going to get produced. And apart from that, we have to discuss on something on the butanol, which is another one kind of the bioalcohol or the biofuel that is produced through this fermentation process. And we need to discuss on some sort of the concentrating procedures. So this keeping it aside, we will deal more or concentrate more on energy production from this lignocellulosic biomass based waste or any kind of the organic waste through transesterification reaction. So that is the predominant focus for this particular week 7 live interaction session. So speaking of the trans-esterification reaction, it is nothing but you have this organic waste which basically consists of the triglycerides. So this triglycerides, when you use alcohol or when you use some sort of an alcohol like methanol or any other higher alcohols, this glyceride as well as this ethanol or any kind of alcohol is going to react to give fatty acids of the alkyl esters and glycerin as the main product. So this particular fatty acids of the alkyl esters are going to be used for your energy production, or it is going to be used as a biodiesel for the production of energy. So that's what is the basics of this trans-esterification reaction is. That is, you are going to use triglycerides as your uh, as a component of the organic waste, or you're actually going to derive this triglycerides from the organic waste material, and then you're basically going to react that with the alcohol to produce glycerol and fatty acids of the alkyl esters, which is going to be used as a biodiesel or biofuel or anything that is meant to produce energy. So let me just write that triglycerides plus, I'm going to keep it as alcohol here because it's not necessary that you should use only methanol. You can also use alcohols with the higher carbon numbers or higher alcohols. This will give fatty acids of alkyl esters plus glycerol. So this is the basics of the trans-esterification reaction, you can say, or you can also call it as uh, the trans-esterification process reaction mechanism. So this process is commonly used for the biodiesel production, as I said, and this usually happens in the presence of a catalyst. So what could be so what are the catalysts that is used for this particular trans-esterification reaction?
Sodium hydroxide or potassium hydroxide.
Yeah. So they are so base catalyst, which is sodium hydroxide or potassium hydroxide. But then the using this catalyst has a issue. So I hope everybody, since it is there in the course content also, everybody will be aware of this. So there is one particular limitations of using a base catalyst for this trans esterification reaction. So what are the limitations? of this catalyst? Yes, limitations of using potassium hydroxide or sodium hydroxide for this transesterification reaction. Yeah, but mm, mm, yeah, so to avoid soap formation, so that is the to avoid soap formation, or you can say the sodium or potassium salts of that alkyl ester, so that is nothing but is actually soap. So what happens is that this, when you are going to extract triglycerides from this organic based waste or organic waste, there are also chances of that the free fatty acids are also present along with this triglycerides. It need not always be. Yes. uh, uh excuse me, can you just come back, because I didn't, your voice was not clear. Okay. So I was asking about this. Okay, so if you don't mind, could you just type in you know, your response in the chat box, because your voice was not actually clear. So, hmm. So you just type in the chat box. Uh, so where were we? Yeah. So this was typically to avoid the soap formation. As I said, that triglycerides are also, I mean, the fatty acids also gets into the picture when you are going to extract the triglycerides from the waste material. So there is sort of like it is going to be present along with this triglycerides. So in order to, so when this free fatty acids are going to be present, when you use sodium hydroxide or potassium hydroxide as a catalyst, as somebody rightly said, the fatty acids are going to react with this base catalyst to form the sodium or the potassium salts of the fatty acid alkyl esters, that they are also called as soap. So this to prevent the formation of the soap in the product, or to prevent the contamination of the soap in the product, we tend to use catalyst other than this base catalyst. The reason why soap formation is not advisable in case of this process is because it actually tends to. Yes. Okay. We are discussing on this, what do you say, um only for this, I mean the basics of this trans esterification reaction, so that methanol recovery we will discuss as we go, further in the discussion. So yes. um so the reason why we need to avoid the soap formulation with the product is because soap as such will it will degrade the quality of the fuel. So it will bring down the fuel characteristics, or basically the properties of the fuel, which will impact on the energy efficiency or the energy content that is there in the fuel. So that is the reason why this soap formulation needs to be avoided. And one of the ways to avoid this soap formulation is to make sure that you do not use base catalyst. You also use other catalysts such as acid catalyst, or you use some sort of a heterogeneous catalyst, because potassium as well as sodium hydroxide is a homogeneous catalyst. So we can tend to use some other catalysts such as the heterogeneous catalysts. Of course, there's a lot of development that is going on in the field, as such it is also mentioned in that course. So we have the liberty to vary this kind of the catalyst, so that we can improve upon the properties of the fuel that we are going to obtain. So this is about the what do you say, kind of a picture on this transesterification reaction. So there are multiple sources for this, for getting this triglycerides. So how to obtain triglyceride, or sources of triglycerides? So the first one is you have waste oil, then recycled grease, and then the third one is waste oil seeds. So in both this, in the case of 1 and 2, waste oil and the recycled grease, the concept is pretty simple, because you can, because already these waste oil as well as that of the recycled grease contain triglycerides in them. But however, that is not the case with the waste oil seeds, because they are in the form of seeds, and you need to extract the oil from those seeds, and then you need to use that oil for the transesterification reaction to obtain this fatty acids of alkyl esters, or you can call it as a biodiesel. So this basically requires a kind of an extra process for for bio oil production. So that is one of the kind of, you can say, extra process that is required to obtain this biodiesel. So this is about the sources of the triglyceride. So once you have this waste oil seeds, and if you need to extract the bio oil from them, there are different process or procedures to follow, or you can say different processes to obtain oil from these seeds. So there are two different processes, or the major classification is of two different types. One is the conventional methods, and another one is the advanced methods. So what are the conventional methods, and what is this advanced methods? For extraction of oil from waste oil seeds? Yes, this is, I think, it is there in the, it is a very direct question that is there in the lectures. Conventional methods and advanced methods. Yes. So in the conventional method, we have two different types of techniques. And of course, in advanced also, we have two different types of techniques. So we have something called expeller press method, and second one is solvent extraction method. And in case of the advanced method, just a second. Sure. Yeah, just sorry, some disturbance. Uh, my presentation is visible, right? Okay. So, what are the advanced methods for this oil production from this seeds? Uh, yes, supercritical fluid extraction. Yeah. So, the expeller press method is typically a physical technique, so wherein it's just very simple. You take the seeds or you take the oil seeds and then you just put pressure on top of that. So because of the physical pressure, what happens is the seed, the cell, the seed burst, the cell and the cell wall burst, and then the oil gets extracted out from the seed. So that is very simple technique. It's just that you are going to apply pressure on the seeds to extract the oil from the seeds. Whereas in case of the solvent extraction method, what typically happens is you are going to use some sort of a solvent in the system to extract the oil from the seed. So you basically use some sort of non-polar solvents. So for example, you can say, I think, butane or pentane. And then what you can do is you can keep the seeds in them. And then because of the solvent action, what happens is the cell as well as that of the cell wall breaks because of the solvents. And then the oil gets extracted out from them. It basically comes out of the cell and mixes up with this solvent, after which a post treatment process is carried over, wherein this solvent as well as your oil is going to be separated out, so that this particular oil that you are going to get can be used for your transesterification process. So these are the conventional methods for this oil production. However, in case of advanced method, you have something called ultrasonic assisted and supercritical fluid extraction. So the principle is going to, I mean, the motive is going to remain the same. That is, you need to extract the oil from the seeds, but then the procedure keeps varying in all these four methods. In case of expeller press, you use physical pressure, or you put pressure on the seeds. In case of the solvent extraction, you use solvent. So can anybody, like, just kind of, you can even say, you can guess what is this ultrasonic assisted method could be? Like, what do you think could be the major principle behind this ultrasonic assisted oil extraction method, or how do you think this will actually work? ultrasonic assisted extraction method. What do you think would be the what do you say? Kind of what do you think this method could be based upon? Like previously we had pressure, solvent. What do you think would be the main source for that would be responsible for oil extraction from these waste oil seeds? Uh, so it is basically the ultrasound waves. So what you do is yeah, ultrasound waves, they basically carry energy. So because of that energy, what happens is so that amount of energy that is going to be carried by these waves is going to be huge. So because of that energy that these waves carry, the cell wall breaks, and from there the oil gets extracted. So this is about the ultrasonic assisted extraction method. So now the question is, so we are actually going to use something so called as a biodiesel, or as such it will be in the form of like an oil only. So what could be the reason for going for an extra process here? Like you take waste oil seeds, and then as I said, I'm going to produce bio oil from them, or I'm going to extract oil from this seeds, then use this oil for the transesterification process before using them what do you say, before using them as a biodiesel for any of the application. But what is the need for this long process? Why can't I just take this bio oil, instead of doing any sort of the transesterification process, I just directly blend them with gasoline or any other kind of the fuel that is previously available and use it for my application? What do you think? There is a requirement for such a long process. Why can't I just bypass? Yes. Yes. Hmm. So viscosity, yeah, viscosity is high, or is it I mean low? Yeah. Hmm. 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 So hmm. Yes. Yeah. So miss all sorts of fuel properties, you can say. And then anything else? Mm-hmm. So yeah, that's exactly right as Sir told. So what the thing is, the oil that you're going to extract from this seed is going to be highly viscous. So viscous as such, what we mean is it is going to be very thick, like in the sense it is basically becoming very difficult for that particular fluid to flow. So due to that, what happens is when you actually use these oils directly in case of any of your application, pumping this oil becomes a big issue because it's going to be so viscous, so thick, or how can you say it, going to be so mm, thick, uh, and it has a resistance to that flow. So because of that, the expensiveness of this process is going to increase. And one more thing is, what happens is this particular, since the viscosity is going to be so high, it cannot actually break, the oil cannot break it itself into droplets. So because of that, due to all these reasons, specifically the viscosity, the combustion will be inefficient. So because of the inefficiency in the combustion process, what happens is you require so much amount of oil to produce a very little amount of energy, which is economically infeasible. So that is the reason why you have a trans-esterification process or some sort of an upgradation process to this bio oil before we use it as a biodiesel in some for some application. The so what we can actually infer from this is the amount of what do you say, energy or the cost that is required to do this long process is much lesser compared to directly using this bio oil for this energy production. So this is the reason for this, why we require a intermediate or something so called as a trans-esterification process for using this bio oil as a biodiesel for our applications. Now, the thing is, so as such, again, we always, as we discuss, for any processes, there will be factors which will be affecting the system. So, what could be the factors that will affect the, you can say, factors which will affect this solvent extraction process? You can say any extraction process as such. So, let it be as wide as possible. Just a second. Yeah, one, then, and then, okay, temperature, extraction method. So, yeah, that typically depends whether you're going to use physical or you're going to use any solvent. Yes, extraction methods and time. Just a second. Extraction time, moisture content, particle size, and shape. So again, if you're going to use some sort of this expeller press method, then I guess pressure will also be one of the thing that you need to optimize, so that the amount of oil or that you can extract from this particular seed will be more. So in this case, so talking about the, so you need to maintain the temperature, so that the temperature, so how does it vary? So if your temperature is high, then the amount of oil that is going to be extracted from the seeds is high. But what happens if the temperature of that process exceeds the boiling point of the oil that you're going to extract? It will just vaporize. So at that point of time, you will not have that, so since it's going to vaporize, the yield will is going to actually decrease. Apart from that, you have time. So more time means more extraction of oil, so increase in the yield of the oil production. Then particle size and shape. So if your particle is as small as possible, then what will happen is you will have more surface area, so more contact, so extraction is more feasible in that condition. So this is about the extraction, and then once you do this extraction, it is similar to that trans-esterification process. You are going to obtain the biodiesel at the end. So this biodiesel is typically, less hazardous, as you can say non-hazardous. So properties of biodiesel. non-hazardous, or you can say this has advantages also, non-hazardous. Then any other, you can say non-toxic also. Apart from that, you have,
So
okay, yes, yeah, yeah, yeah. And then, so air pollution is less because of this process. Air pollution is minimized. So yeah, these are the typical advantages of, you know, getting a biodiesel through this trans-esterification process. So you can have a non-hazardous, non-toxic, and with the minimal or more environment-friendly biodiesel compared to the other techniques that is used. So once we have this biodiesel, we need to characterize this biodiesel. You have terms like, so let me just give out the list here. Let me just write the list, and let's see how many, you know, I will, you guys can tell me what does that particular property actually mean. No, no, so I'm just giving you guys, just respond back on what does this property actually mean. Like, so we are going to now characterize, we have produced the biodiesel, we are going to characterize that biodiesel. So first I'm going, of course we have this ash percentage, but those are all, that is something that was discussed I think in the first session also. So let's focus on something for this specific, especially that is there for this week 7 course content. So first is the cloud point. So what is a cloud point? Like, temperature at which the biodiesel becomes like hazy, sort of like becomes, hazy, or gives a cloud like appearance, you can say. So this is the cloud point. Then you have something called pour point. Yeah, so anything, so this is basically the temperature at which the biodiesel can pour, or you can say can flow. Flow, because beyond this temperature what will happen is the entire biodiesel that you're going to have is going to actually get solidified. The flow will get freezed. So you can say this is the temperature at which that particular, you can say that the liquid flow will start to cease. So then we have something called flash point. Yeah, so it is. Sort of something like, at which the ignition starts to happen. So as such we will write here temperature at which it starts to flash, or you can say ignition just starts to happen. Then we have something called fire point. Yeah, so it starts to fire, the temperature at which the fuel starts to fire. So any idea on how do they actually measure these kind of points? Like, I mean, yeah, we do have certain things to discuss beyond this, but before that, any idea on how this cloud point, pour point, flash point, or fire point is determined? Like, but yes, that's exactly what I mean. It's a very simple experiment, but that also have typical standards to maintain. So, any ideas on what kind of standards or who sets those kind of standards for this particular? Yeah, experiment is right. So you just take a certain amount of sample, a known quantity of the sample, and then you tend to decrease the temperature of that to basically identify at what is the point that cloud hazy nature comes, and at what point the biodiesel or the oil, whatever you're going to take, is going to completely cease its flow. But what kind of standards do we use for that? Yes, ASTM standards. And I hope any ideas on the full form for ASTM? Testing and materials. So ASTM, is a kind of an American society which basically, what do you say, they sort of devise the standards for detecting this cloud point, pour point, flash point, and fire point. So there are lots of videos that is available on YouTube on how this particular calculation of pour point and cloud point is usually done. So you are always welcome to just type this in the YouTube or in Google. Then you will be able to get a quite a good number of videos where you can see how this is actually determined. So after this, you have heating value. I hope everybody knows this is a very, for us now it has become a common thing since we are discussing this for almost like 7 weeks till now. So anyway, heating value, the particular definition. So the reason why we are discussing is there are chances that these kind of questions can come in assignment or your final exam. So that is typically the perspective, so that we just revise everything once again of what we discussed in the course over the week. Yeah. So it is typically nothing but the energy that is contained in the fuel, or you can say the amount of energy that is released when the fuel is burnt per unit mass of the material I mean, the fuel that you're going to use. So energy content, you can say energy content of the fuel, or energy contained in the energy contained in the fuel per unit mass. So this is the heating value. So these are the typical, what you can say is the sort of characteristics or properties which deals with the physical nature. Like these are the physical properties. So except for this heating value, this fire point, flash point, pour point, and cloud point. Now we have something else also in the list. Do we something so called as iodine value. What is the purpose of determining this iodine value, and how do you do that? To determine the degree of unsaturation in the. So what we typically do is we actually take this biodiesel, and then we basically make them to react with ICl, iodine chloride, or IBr, iodine bromide. So they react with them, and what happens is, if you have a unsaturated what do you say, fatty acids, or unsaturated that alkyl esters, if it is unsaturated, it will break, the ICl will break that unsaturation, and the iodine molecules will get added to the hydrocarbon, releasing I2. So this, yeah, so if you have any excess of ICl that you are going to use in the system, you take the system and then you basically make it to react with the potassium iodide, which will again release I2. That I2 is made to react with the sodium thiosulfate. So depending upon the amount of the iodine that is going to react, you can back calculate to understand how much amount of the ICl is consumed to determine the degree of the unsaturation in the biodiesel. So this is typical, that basic titration techniques what we use in the lower grades. So that is how you determine the iodine value of your biodiesel. By iodine value, what we mean is the degree of unsaturation in the compound that we are interested in. After this, we have something so called as acid value, but we will not discuss that for the time being, because we have some MCQs related to that to discuss. So at that time, we will cover that as well. So let's talk briefly about this recovery process. So as somebody was saying quite some time before also, about that methanol recovery. So what happens is, you need to separate this. You have alcohol, fatty acids, and glycerol. So you need to remove this, and also if you use a base catalyst, you are also going to get soap in the system. So you need to remove this, you need to separate them, you need to get separate methanol or any alcohol that you are going to use. You need to separate the fatty acids of the alkyl esters, that is going to be a main component as biodiesel, which needs to be pure. And then you are also going to separate this glycerol. So for that, each process we have a different way of doing. So for this methanol recovery, I think you particularly go for this super critical fluid extraction techniques as well. So the question is, so each and everything has a typical way of separation. So can anybody tell me why do we need to extract this methanol alone from this system? Like we do extract, we can understand that because you need to keep your biodiesel pure. But what is the need for separating this ethanol? Sorry, what is the need for separating this alcohol from the mixture? I think this slide is not necessary. So it is simple. So one thing is the cost, and another thing is if the alcohol is going to be there present within the system, there are also chances that this fatty acids plus glycerol, that reaction, whatever you see here, can actually reverse. So in that case, what will happen is the content of that biodiesel that you are going to produce through this transesterification is going to decrease. So the efficiency of the process is going to decrease. So that becomes a process, or that becomes a need for removing this methanol out of the system. And the reason for separating the glycerol is because glycerol as such, it's a byproduct here, but it has its own values. So there are a lot of applications of glycerol. So if anybody has any idea, one or two examples of where we use this glycerols in the system. So you can always look out, sorry, in the practical, what do you say, in real life uh, applications, I'll write. So glycerol is typically used in a variety of other applications also. So if you are interested, you can always look at them, and then yeah. So here we end with our discussion. So before moving on, so next we have some MCQs to discuss. So before that, if you have anything that you want to discuss related to what we have just went through now, then you are welcome to do so. Yes. Hmm. Yes. Hmm. 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 So I am not exactly very sure about how they use. I mean, what is that process actually? That step by step process. So actually, this is a very you can say evolving field. So people are using. I mean, there's still the research is going on how do you use this cooked oil. I mean, the waste oil for this biodiesel production. I mean, there are a lot of research paper as such. So I am exactly not very sure right now about the exact process of converting this cooked oil or the waste, the oil that gets generated into the homes as a biodiesel. So if probably I think we can discuss that in the next class, or I can just incorporate one slide here, and then I can give a graph, I mean sorry, a schematic wherein I can write whatever I come to understand after going through that process, after going through the contents of that. Yeah. So so the first question, I think these questions could be quite simple. So anyway, let's do. Identify the, I mean, it's just basically you need to tell me what is the formula for this ethanol yield calculation. So that's what is given. Identify the appropriate options for ethanol yield calculation, where C is the ethanol concentration, V is the initial volume of liquid, and M is the mass of the substrate. I hope there is nothing, doubt in this question, because it's a straightforward formula. So CB by M. This is the ethanol yield. So next question is, the microorganism ingests carbon monoxide, carbon dioxide, and hydrogen, and mostly produce biogas, butanol and water, ethanol and water, sugar and alcohol. Water. So here, so as such, option C and B cannot come, because this sugar and alcohol, so those two are completely two different, what do you say, compounds, or in the aspect of this fermentation, sugar is something that is going to be as your reactant, and alcohol is what is going to be generated after this microorganism act upon that. So that is the reason option C is wrong. Option B, it cannot be biogas, and option A is butanol and water. So yeah, so this also could be, but again the text actually says ethanol and water, so we go with that. And then here we have another question: traditional method of butanol recovery for from the aqueous fermentation broth. So it cannot be fermentation, because fermentation is a process wherein you're going to actually produce butanol, and the liquid extraction is also not possible in this case. Well, it is one of the method for butanol recovery, but it is not the traditional method as such, because it is given the word traditional. So that the option will be C, that is the distillation. Again, I guess this question, the first one is a very direct one. Which one is an advanced method for production of bio oil from oil seeds? Fluid extraction method. So, as such, this supercritical fluid extraction and ultrasound assisted comes under the category of the solvent extraction method. But as such, the solvent extraction method is a conventional method for the production of bio oil from seeds. So, typically speaking, you have the conventional solvent extraction method as such, but the more advanced form of this solvent extraction method is going to be a supercritical fluid extraction technique and ultrasonic assisted extraction method. So next we have, which of the following is an indicator for the determination of the acid value? So the question is, which of the following is an indicator that is used in determining the acid value? Okay, any other response? It cannot be iodine because you do not use iodine in determining the acid value of the system. That is something typical for your so that's something that is used for calculating the iodine value of a particular fuel. So is it going to be, so both are indicators here. So apart from iodine, for this case, apart from iodine, phenolphthalein and methyl orange both are going to be both are an indicator, but which one is right? Somebody has told methyl orange. Is it okay, or is the answer phenolphthalein? Yeah, so typically the acid value is used to determine the conversion of the free fatty acids in the system. So what you do is you take the sample and then you dissolve it in ethanol, and then I think you titrate it with the potassium hydroxide as a system, for which you use phenolphthalein as an indicator. So these kind of questions can actually confuse. So that is the reason why um, it is we are discussing this here, because as such when you see methyl orange and phenolphthalein, people tend to it is very common that we confuse ourselves. So it is phenolphthalein is the answer. So yeah, acid value as such, we I just told right now, it is basically for determining the percentage of conversion of the free fatty acids in the system. So if you are going to take what do you say? If you are going to take the fatty acids, we have to know how much of them is going to be converted, and for that process we define a value so called as an acid value. Next, so you need to see this diagram and then say, identify that method for the recovery as shown in this figure. Supercritical. And for which particular, you can say biodiesel or biofuel, this recovery process is used? Oh, so this is typically, it's a supercritical fluid extraction process. So yeah, that's fine. It's my mistake. Okay, yeah, correct. So because you can use this for any kind of oil extraction process, then The most common and traditional microorganism used for fermenting sugars into ethanol. It's a yeast. So that is the, you can say, sort of clue. It's a yeast. It's a very common one which is used in this, what do you call? Mm, in this bakery products and stuff. So it's actually called as a baker's yeast or brewing yeast also. You can say that is another one. This thing is, it is typically only for this. What do you say? Glucose alone. It is used for hexose. So it is called. Let me just write Saccharomyces cerevisiae. So this is also called as such as I said, this is also called as a baker's yeast, brewer's yeast, which is used for fermenting of sugars, specifically the hexose into ethanol. So that becomes one of the limitations for using this microorganism, or you can say this yeast, because it can only go for hexose and sometimes for some sort of a pentose, but it cannot be widely used for other complex sugars. So depending upon the type of the sugars that you use for the fermentation process, the kind of this microorganism that you're going to use for the process also differs. So that is what is also there in one of the other kind of in this biological conversion routes itself, you have some microorganism called clostridium, and I'm not exactly sure of the term clostridium. And does anybody remember that particular microorganism which is used in this biological conversion routes? Yeah. So so among them, the most common and the traditional microorganism is the Saccharomyces cerevisiae. So this is a straightforward question. It's just that we need to know what is that particular microorganism that you are going for what process. Next, match the following. So you have sugars on the left hand side and their formulas on the right hand side, so you need to match. You have cellulose, cellubiose. Okay. Okay. Hmm. So this is just for, like, I mean, yeah, that is right. So let me just yes, 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 sure. Yeah, that's Yeah, that is true. So have I written? Just a second, 1 minute. That's correct actually. Just a second, 1 second. Hmm. So this should be okay. So let me just keep this question for the time being. Yes, it's right that C6H12O6 should be for cellulose. Sorry, for glucose, and cellobiosis O11, and xylose is C5H10O5, right? And xylobiosis C10H18O9. Okay, okay, okay. Yes. So is this fine? So 1 will match with S, 2 will match with R, 3 is going to match with Q, and 4 is going to match with T. So we have one, this is a straightforward question. You just need to guess the, I mean, what do you say? Tell me the equation for the conversion of the free fatty, of the FFAs and the acid value. Uh, Valsa Kumari madam, I think you can just yeah. So this is nothing but S of O, that is minus, sorry, minus S of I by S of O. So here SO is nothing but it is the initial acid value, and Si is nothing but the acid value at a particular time, at a particular instant of time. So this is the conversion. What do you say? How? What is the conversion of that fatty acid? But this, to calculate this acid value, we have a formula. So which is nothing but, just a second. Yeah. So the equation for this acid value, that is as such, S is nothing but 56.1 times V times C by M. So here M is nothing but the mass of sample that you're going to take for analysis. V is nothing but the volume of KOH, and C is the concentration of the KOH. But my doubt is, what is this 56.1 that is there as a factor here in the acid value calculation? So V is volume of KOH, C is concentration of KOH, and M is mass of sample for analysis. What is that 56.1 which is there hanging. Yeah, yeah. KOH, molecular weight of KOH. One gram per mole actually. So that is the molecular weight of KOH that you are going to use. So since you're titrating it against the KOH, we do need to incorporate that molecular weight of KOH into the what do you say, that formula. So that ends the discussion on this the theoretical based questions. So anything that you would like to share here before we have I guess two to three of 3 or 4 questions that is pending. Hmm. Okay. Hmm. Yeah, I get it. I get it. Hmm. So what we will typically do is as far as I have an understanding on this, so we will initially take a known quantity of the sample. So we will have the bio oil, and then what we are going to do is we are actually what do you say? We will actually, so this will typically happen within as the reaction is progressing. So you have this triglyceride and ethanol that is going to react in the reactor, and then uh, as the reaction continues, you will also have this product that is going to get generated, that is your fatty acids of this alkyl esters and your glycerol. So what you do is, before the reaction starts, you are going to take a known quantity of the sample from the system, and then you are going to, again as I said, react it with the potassium hydroxide and calculate the S value from that. So as the reaction is progressing at every instant of time, so after every regular instant of time, let's say, I mean, depending upon the reaction, so you're going to take at different instances of time at regular, intervals of period. You're going to take the same known quantity of the sample and do the titration as such what you have done before the reaction starts, and then you're going to calculate that value. So you now have your S naught and Si at certain instant of time. So like that you will calculate at every different instance of time, because that value what you're going to see is going to differ. So that's how you will obtain this S naught and Si value, and with that you can calculate this conversion of fatty acids. Hmm. 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 Yeah, we will prepare a standard solution. Yeah, as I said, some XML of hmm, yes. So you will, yeah. So what you So okay, so what you will do is you will actually take the sample in the, you can say, in a in a flask or something, and then this KOH will be there and the burette. So in this sample itself, you will add that phenolphthalein indicator. So once you add that phenolphthalein indicator, what or just a second. Yes. So in that flask that you're going to take itself, you will add that phenolphthalein indicator. And then in this burette that I hope so you will have a burette. So where you will fill around 50 ml of KOH of a known concentration. So you will slowly, yeah, 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 hmm, hmm, yeah, yeah. And then you stop that adding of KOH at that point. Yeah, so, hmm, yeah, 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 exactly. So once you stop the burette, so you can see how much amount of the KOH is consumed up for this reaction, and then using that, so now you have the V, the V, C as such because you prepared that standard solution. M, because we have taken it from our reaction system, and so with that, with this formula, you can calculate the acid value. Yeah. Yeah, yeah. So let's go on to some questions. Again, as such, it's a very standard question. It's a practice session, so we will take up with some of the questions where we require more practice or something very typical to what is done in the course. So, during the pre-treatment process, 60 percentage of the lignocellulosic waste biomass is converted to monosaccharides and disaccharides in the mass ratio of 3 is to 7. The monosaccharides produces 600 grams of ethanol per kg of monosaccharides, and the disaccharide produce 500 grams of ethanol. Calculate the total yield of ethanol in kg. Instead of saying the word yield, I'll write calculate the total amount of ethanol obtained in kg. It's a very, what do you say, kind of a straightforward question. So let me just write the initial steps, and in case if you have the answers ready, then you're welcome to give the answers. So 60 percentage of the mass of a lignocellulosic waste. So since we do not have a base here, as we do regularly, we take the basis, which is nothing but 100 kg of waste. And if you ask why 100, then it's basically to make sure that the calculation is relatively more simple. So out of this 100 kg of waste, 60 percentage is going to be converted to monosaccharides and disaccharides. So that means 60 by 100 of this 100 kg waste is going to be converted to monosaccharides and disaccharides. So that is nothing but 60 kg is going to be converted to mono and mono and disaccharides. Okay, so I'll have to check. So you say 31.8, right? Is that right, ma'am? Okay, okay. Let us calculate. Yeah. So here mono is, so you have 3 is to 7. So that you can say mono is 3 parts of the total mono plus di. That is 3 by 10 times of this 60. So that is nothing but 18 kg of monosaccharides, and you have di, which is nothing but 7. So 7 parts. So 7 by 10 times 60. So that is going to be 7 6 are 42. 42 kg of disaccharides. So for every kg of monosaccharides, 600 gram of ethanol is going to be produced. 600 gram of ethanol for 1 kg of monosaccharides. So if this is the case, then for 18 kg of the monosaccharides, you will be having 600 grams. So let me write it as 0.6 kgs times 18. So zero point 0.6 times 18, which is nothing but 18 6 are 18 6 are is 108. So 10.8. So similarly, 500 grams of ethanol for 1 kg of disaccharides. So for 42 kgs, it will be nothing but, let me just write, right? It will be nothing but zero point 0.5 times 42. So that will be nothing but 21 ethanol. So we are asked to calculate the total amount of ethanol that will be produced are obtained in terms of kg. So total will be total ethanol in kg is nothing but 21 plus 10.8. So that is 31.8. Yes, that's correct. Ethanol is going to be produced in the system. So let me just extend the question. Apart from calculating the total amount of ethanol, also calculate the what do you say? Also calculate the yield of the ethanol. So if I want to calculate the yield from here, what are the other parameters that needs to be there in the question to solve the problem? Yes. So C and V, if you multi, C is concentration, so that is going to be milligram per liter, and volume is again liter. So both will be same. So you can say CV is nothing but the mass of the ethanol. So that will be 31.8. Apart from that, you have something so called as the M, which is there in the denominator, which is called as M is the mass of the substrate. So we need to know the mass of the substrate to calculate the yield of ethanol in the system. So yeah, I mean, I don't want to actually calculate that now, because since I do not have that term here, just that I wanted to, like, know, like, I mean, get this thing from the audience on what kind of parameters are also required if we have to calculate the yield. So that was the main purpose. But yes, apart from that, 31.8 kg of ethanol is the right answer. I hope others also got the same thing, and there may not be any doubts related to here, but if you have, then always welcome to let me know. Yes, yes, exactly. In that case, I will be, yes, yes, okay. In that case, I can get. I will be giving you the concentration of that. What do you say? Sugar in the waste. Actually, there is a question which is similarly that is there in your tutorial section of fermentation, if I am not wrong. So if you can see that there it is given that waste material consists of that 8 percentage of the content as the concentration of the sugar. So they have based on that 8 percentage, they have calculated. So for 100 kg of the waste we are taking, the concentration of sugar is 8 percentage. So 8 by 100 times 100, that is given as 8. So yeah, again, you can also ask me. So we need volume, but what is the thing is, if you are going to calculate concentration of ethanol from here, you are again going to divide that with the volume of the solution. So that will be like C times V. Yeah, exactly. So let's go for the next one. That will be pretty. I guess it will be lengthy, I suppose. But again, a very straightforward, direct questions. So this is for the anaerobic digestion process for production of biogas. So in the industrial biogas plant, food waste is anaerobically digested to produce biogas. Slurry contains 20% of the solid food grains. Okay. Elemental composition is 50 percentage, hydrogen is 10 percentage, oxygen is 30 percentage, and nitrogen is 10 percentage on the mass basis. That's fine. So that will be easy for us. Then around 90 percentage of the food grains is going to be converted to biomass. Oh, sorry, biogas. And all the converted hydrogen forms methane. Flow rate is given 600 liter per day, and they are given us the density of the slurry also as 1 kg per liter. We are asked to calculate the amount of methane produced. So here I think it is going to be quite, I mean, you don't need to assume anything as the basis because they are giving flow rate of slurry is 600 liter per day, and the density of the slurry is given as 1 kg per liter. And we need to calculate the amount of methane produced per day. So let me make the question more clear. Yeah. So if you have answers, then you're welcome to tell me. So let me also start solving. So here we have flow rate. First is flow rate of slurry is 6,000 liter per day. And since we are asked to calculate methane produced per day, so that basis that I am going to keep it as everything what we are going to calculate is only for a day. So here, since density is 1 kg per liter, density is given as 1 kg per liter. So which means it would be 600 times. So it will be mass of the slurry will be 600 kg. If the mass of the slurry is 600 kg, out of that 20 percentage is going to be the solid grains. So 20 percentage of that 60 of that 6,000. 1,200 kg of solid food grains. Now this is going to be convert, so the elemental composition is also given. So let's calculate each one of them. So you have this carbon, so that is 50 percentage. So this is for the food grain. So we have 1,200 kg of solid food grain, and out of that 50 percentage is carbon, and everything is going to be on mass basis. So that will be nothing but 0.5 times 12,000. So that is 600 kg of 600 kg of carbon. Hydrogen is zero point 0.1 times 1200, that is 120 kg of hydrogen. Nitrogen will be same, uh, and you will have another one is oxygen. So that is zero point 0.3 times 360 kg. So this is the elemental composition of every of the particular food grains that we are taking. Now it is written that around 90 percentage of them is going to be converted to biogas, and all the converted hydrogen forms methane. So which means that carbon is going to be converted to biogas. So out of that 600, 90 percentage is going to be converted. So that is 0.9 times 600. So which will be 540. And your hydrogen is also same thing, 0.9 times 120. So that will be 108 kg. Do we have space? So this is the individual carbon and hydrogen that is going to be converted to your biogas, and it is written that all the hydrogen is converted to methane. So methane is CH4. So if all the hydrogen is converted to methane, then what it would be? It would be like, is this fine? So that would be 4 times 108, so 432 kg. So the carbon that is going to be, used up for methane can be calculated as 12 by 16 times of this 432. And how much is that? Just a second. Let me use my calculator here. Yeah, 324. 324 kg of uh okay. And this would be of so the amount of methane gets produced is 324, right? Okay. So what is the amount of methane that is going to produce, like after this the process? Okay. 540 minus 320. Yeah. 216. Yes. Okay. Okay. So that will be uh mhm, times 216. Yes. So how much is that? Just a second, 1 minute. 44 by 12 times 216. It is coming 792. Yeah, yeah, yeah. Is it 792 or is it something else? Yeah, okay. So this will be around 4 to 1. 1224 kg, right? Together. Hmm. So this is the, what do you say? CH4 plus CO2. This is the combination of the amount of both methane and carbon dioxide. So what about, so but then the question, if you read carefully, it asks only us, to methane. So that will be 432 alone. So the question actually ends here. But just for the sake of practice, I just extended it. But so amount of methane as such is produced. So that means the calculation ends there itself. So this is just for answer. Yes, exactly. Let me just highlight that once again. Yeah, might be. I mean, I guess in the assignment it is both. This was actually purposefully done. So yeah. I guess here also nothing much to. I mean, anything that is there which is kind of not clear, because this should be a straightforward thing. Yeah, I hope there is nothing much. I mean, confusions here. So, if there is a confusion with related to calculating of this is simply the like, so for every CH4 molecule that you have four. So you have 108 grams of hydrogen and 4 grams is actually there. So you just do that cross multiplication and bring scale up that CH4 content. So this should be straightforward. So yeah, we actually have two more questions. Okay, just let's take up this one and let's see whether, I mean, this is something that is related to week 4 or 5. I'm not sure which week it is, but yeah, let me just read it out and then. But again, it's a same pattern question as it is there in the course. A fast pyrolysis plant handles 1 TPD MSW and produces gas, char, and liquor. Operating temperature and pressure of the reactor are 788 degrees Celsius and 1 atmospheric pressure respectively. The gas volume percentage of H2, CO, CH4 and CO2 is given. The mass production rate of gas, char and oil are 33, 25 and 42. Determine the product distribution with the individual component of gas and the rate of hydrogen production, assuming 87 percentage separation. So we don't need to actually solve this right now, but can you just give me the flow, the process of solving this question? Okay, okay. Yes. That is the reason I just told it's okay if we don't solve, but can you just give the flow, like how do we need to go about this question? Okay, okay. Hmm. Then you actually, what do you do? You basically try to calculate the molecular weight of the gas that, yeah, and then you calculate the, yes, yes, mm, mm, yes, ma'am. Then, mm. So yeah, that is correct. So that's rate of hydrogen production and product distribution. So yes, so oh, that's correct. Actually, it's a quite a lengthy one, and we are running short of time. So you, yeah. So you can do one thing. We can take it because since the next class will be, it will be kind of the last session for this live interaction. Anyone can take up this problem and then can, if possible, they can, solve it in their what is I mean, whenever they have free time, and can present that in this live interaction session to all the others who are going to attend the next one. So it's just that you need to solve and then just give a sort of, yeah. Hmm. Yeah, okay, that's fine. So So, I mean, yeah, so for this week, I just planned on another one more question, but again, so yeah, that is not an issue. We may cover that up in the summary session that will be there. So, let me just stop my screen, stop presenting. So, for those questions which are, like keep on we try to postpone because of this time issues, there will be a live interaction session after the week 8. So I guess exam is on March 22 if I'm not wrong, so probably by March 17th, if I'm not, yeah, March 17th we will have a summary session that will also be for 2 hours. So during that time we can take up all the remaining questions which were what do you say, kind of getting keep on getting postponed because of this time issues and stuff. So yeah, so that's all for today. If you have anything to discuss or if you have anything to let me know about this, actually, I should suppose I am supposed to ask it every after every session, but if you have any feedback that you like to tell me, then you are welcome to do so right now. Oh yeah, sure. So I am primarily working on conducting polymers, and the application which we are focusing is on the energy storage application. So mainly for batteries and supercapacitors. Okay. Yeah, 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 energy storage. So if there is nothing else, then I think we can conclude the session for today. So yeah, thank you. Yeah, thank you everyone for joining. Okay, okay, yes, ma'am. So thank you for joining today's live interaction session. Uh, I hope this session was useful for everyone. The recordings will be available soon. So you can also access the recordings. And in case if you have any question, my email ID is given in every single. So in the last week when I saw that was missing, so I have updated my mail ID and the front whatever the front page of every single presentations that I'm uploading. So you're always welcome to email me. Yes. Yeah, yeah, I did see your email. It was written as a test email, but I was not sure what. Oh, okay, okay. You wanted me to actually respond to that. Is that right, sir? I mean, you wanted me to reply back to that email? Oh, okay, okay. Oh, okay, okay. Actually, what was the thing was that email was, yeah, 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 yeah. So actually, it was written, it was a test mail. So I was exactly not sure on what to reply back. So that's the reason. Okay, yeah, but I did receive the email. So if you have any queries, you are welcome to email me. Yeah, 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 okay. Yeah, 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 sure, yeah. So yes, I thank Professor Prasanajit Mondal as well as the SWAYAM team for providing me this opportunity to interact with you all on this Sunday afternoon. Our next live interaction session will be on 16th March. So till then, happy learning and thank you. Have a great Sunday evening and bye.